Hello, everyone. Welcome to today's live broadcast, Think Blank, Clean Chemistry Tools for Atomic Spectroscopy. I'm Laura Bush, the Editorial Director of Spectroscopy, and I'll be your moderator for today's event. We're delighted to bring you this educational web seminar presented by Spectroscopy and sponsored by Milestone. Over 20,000 customers worldwide utilize Milestone's products for microwave acid digestion, solvent extraction, synthesis, and ashing, as well as acid purification systems and direct mercury analyzers for solid, liquid, and gas samples. The Milestone team brings together a vision for the future of science, a passion for technology, and knowledge of applications with the ultimate goal of helping chemists with research and quality control. Milestone's patented technology provides the operator with unsurpassed safety and performance capability through the highest temperature and pressure controls, highest safety, ease of use, fast cooling, and brining efficiency for an advanced instrumentation laboratory. Their consultative partnership approach and the trust of their customers have led to Milestone's becoming an industry expert in a wide variety of applications involving some of the most challenging matrices. Milestone's mission is to enable laboratories worldwide with success, growth, and continuous innovation. We have a few housekeeping announcements before we get started. The webcast is intended to be interactive, so we encourage you to ask questions. You can submit questions at any time by typing them in the Q&A box, and you can find that on the right-hand side of your presentation window. You can enlarge the slide window by clicking on the small green icon in the upper right-hand corner, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the web seminar. If you have any technical problems viewing or hearing the presentation, please click on the question mark Help widget at the bottom of your window. Please also note the valuable resources provided by our sponsor that are located on the right-hand side of your screen. I would now like to introduce today's speakers. We're very pleased to be joined today by Joaquim Nóbrega and Tim Michael. Joaquim Nóbrega is a professor in the Department of Chemistry at the Federal University of São Carlos in Brazil and visiting professor at the Faculty of Pharmacy at the University of Concepción in Chile. Dr. Nóbrega received his PhD from the State University of Campinas in Brazil. His main research interests are sample preparation for inorganic analysis, atomic absorption spectrometry, atomic emission spectrometry, and inductively coupled plasma mass spectrometry. He's the co-author of the recently published book, Think Blank, Clean Chemistry Tools for Atomic Spectroscopy. Tim Michael received his master's in environmental chemistry from the University of Wisconsin-La Crosse in 2003 and began work as an applications chemist for Milestone in 2004. Tim's primary focus and responsibility is to educate and train Milestone's customers on microwave digestion and develop applications for preparing samples prior to ICP OES and ICP-MS analysis. So let's just take a quick look at the agenda for today. Today's speakers will cover the concept of Think Blank, cleaning methods, trace analysis reagents, the role of sample prep in trace analysis, and the Milestone Ethos UP and the Milestone UltraWAVE instruments in terms of how these fit into these concepts. Okay, Dr. Nóbrega, you have the floor.
Thanks, Laura. So, we will briefly talk about clean chemistry tools for atomic spectroscopy. Hello, everybody. Certainly, you know the Clean Chemistry book written by Robert Richter in 2003. It's still a nice source of information about clean procedures in analytical chemistry with practical tips about control of contamination and sample preparation. Recently, we have decided to update it. So, Milestone just published a new book written by Richter, Pirola, and myself. This book has 6 chapters, as you see in these slides. 2 of them are about contamination control. 1 chapter contains a brief discussion about ICP OES and ICP-MS, and the other chapters are related to microwave-assisted sample preparation applied for trace analysis. In this book, we discuss about chemical analysis performed by using ICP OES and ICP-MS. Of course, a laboratory must have full control of analytical blanks and sample preparation for obtaining accurate results. So, in this book, we discuss how to control contaminations and modern strategies for microwave-assisted sample preparation. According to IUPAC, trace element is any element present in concentration lower than 100 ppm. A more broad definition is that trace analysis is any analytical procedure requiring special steps to be taken because of the low concentration of analyte which is present. A nice view was proposed by De Gallen some years ago in a JAS paper. This author stated that chemical analysis is going down to low concentrations along decades, and we clearly see a route from ppm to ppb and then to ppt. Nowadays, we may think about the demands for chemical speciation analysis. However, we know that determination of low concentrations typically presents high standard deviations, and the Horowitz trumpet is a clear representation of difficulties caused by matrix effects, multi-step procedures, contamination, losses, interferences, and noise. In a recent paper describing an interlaboratory study, most participants have mentioned that they had difficulties with sample preparation, and this step was the major source of errors, as we can see in this figure.
Dr. Nobrega, this is Laura. I'm just wondering if you could speak a little louder. The audience is having a little trouble hearing you.
A critical point in trace analysis is to think carefully about the analytical blank. We know that we can add contaminants in several steps of an analytical procedure. In trace analysis, it is always critical to remember that the blank is as important as the sample, and one is useless without the other. We need to look to ourselves as a source of contamination. For example, think about the high concentrations of metals in human sweat, such as zinc, copper, and sodium, as we can see in this table. It is also known that we may add contaminants depending on products we are using, such as lipstick, powder, eyeshadow, and so on. As expected, any experimental detail affects the determination of trace elements. In other words, we should look critically at all general purpose materials to be used in trace analysis. The effects of contamination from air, apparatus, containers, and reagents have become increasingly important as the sensitivity of analytical methods has lowered detectable limits to the nanogram level. For instance, consider the concentrations of trace elements in polymers that we use in labs and their potential for adding contaminants. We see some examples here in this table for polymers frequently used as sample containers. These contaminants may be listed as we see in the second column of this table. In the third column, we see how we can improve that by acid washing the auto-sampler container. We see really low concentrations after acid washing. In this sense, it's important that we use equipment for acid cleaning when we need to go down for really low concentration levels. Of course, acid cleaning has a pronounced effect on analytical blanks. Tim will talk about this later on. The easy and practical purification of acids by sub-boiling distillation is also a critical need. In this procedure, acid reagent is distilled in a temperature below its boiling point, and the vapor gradually formed is condensed in a quartz condenser and collected in a quartz container. We see in the second column of this table how clean is the sub-boiled acid when compared to traditional distillation. Look at the total concentration for each distillation procedure in the last line of this table. Sub-boiled acid is 100 times cleaner than traditional distillation. Of course, this is a critical aspect for ICP-MS measurements. When discussing about microwave-assisted sample preparation for trace analysis, we have mentioned that detection power is improved when working with high sample mass, lower acid concentration, or lower acid volume. Analytical procedures using low volumes of acids were described, and it was discussed how to control the microwave-assisted heating to promote effective digestions. We also discussed how the microwave-assisted heating promotes a gradient of temperature inside the reaction vessel, and how this aspect improves digestion conditions and allows a better control of the increase of pressure. The point here is that microwave radiation interacts with solutions containing ions and dipoles, but interaction with vessel material and vapor phase is poor. It was demonstrated that dilute nitric acid solution, such as 2 molar, can be used for digestion of organic samples. And because of lower acid volume and lower acid concentration, it's possible to work with lower dilution factors. The effect of oxygen in gas phase for regeneration of nitric acid was also demonstrated. Another important technology is the Vent-Reseal Mechanism. For safety reasons, vessels may open to relieve pressure and close again. Richter and co-workers have shown that solutions can be evaporated without losses of analytes, even critical ones, such as arsenic, selenium, cadmium, and mercury. Recently, we have shown that the Vent-Reseal mechanism can be used for digesting high masses of samples without losing volatile elements, as can be observed in table 24 for mercury. In spite of losing up to 27% of solution by evaporation, mercury was quantitatively recovered in tuna fish certified reference material. So, the important point is to control the heating process. The vessel-in-vessel technology was also discussed in the Clean Chemistry book as a special strategy for trace analysis. In the Clean Chemistry book, it was discussed how vessel-in-vessel procedure can deal with high masses of samples without increasing the internal pressure of the vessel. Finally, we discuss about the one vessel principle. The idea here is to keep the sample solution in one and the same vessel during all analytical steps. We have demonstrated how the one vessel principle is implemented using the UltraWAVE with a single reaction chamber. This reactor is a large pressurized stainless steel reaction chamber into which all samples are placed and digested simultaneously. In a paper published in Atlanta 3 years ago, it was demonstrated that the use of single reaction chamber approach allows the implementation of efficient digestion using dilute solutions of nitric acid, and also allows addressing a critical need of sample preparation for inorganic analysis by running mixed batches of samples. In this work, samples of plant and animal tissues or samples of polymer, biodiesel, lubricant oil, lube oil plus biodiesel were simultaneously digested. In all cases, residual carbon contents were compatible with measurements by ICP OES and ICP-MS. In conclusion, it was pointed out that all sample preparation steps for each sample were carried out in only one vial, decreasing possibilities of losses of analytes and contaminations. And we concluded that sample preparation is becoming simple and compatible with analytical capability of modern instrumentation. Thinking about an ideal analytical procedure, certainly microwave-assisted sample preparation is helping ICP OES and ICP-MS to perform accurate trace analysis. Of course, only by using a clean sample preparation procedure, we will be able to exploit the analytical capability of ICP OES and ICP-MS. As mentioned by Barnes, it is believed that ICP sources will continue to be used in the coming decades, and microwave-enhanced chemistry will allow better understanding and control, better blanks, and consequently, proper use of modern analytical instrumentation. We may say that in the past, microwave was seen as a useful tool for fast heating, but nowadays microwave is a powerful tool for improving trace analysis. This is the main point that we stress in this just published book. Thank you very much for your kind attention. Back to Laura.
Thank you very much, Dr. Nobrega. Before we move on to Tim's part of the presentation, we have a quick polling question for all of you in the audience. You can answer the question by clicking directly on your screen. And you can see the question up on your screen now, and it says, in your laboratory, do you use ultra-pure acids for sample prep? Yes or no? So once again, you can click directly on your screen to answer. In your laboratory, do you use ultra-pure acids for sample prep? Yes or no? All right, let's pull up those answers. So it looks like just under 70% of you do use ultra-pure acids for sample prep. Okay, Tim, over to you.
Great. Thanks, Laura, and thank you, Dr. Nobrega. So I think one of the themes of today's presentation is obviously controlling the analytical blank. And Milestone came up with the slogan, Think Blank, because doing so is almost a state of mind that the analyst needs to be in. One must ask themselves, if I do this or don't do this, what is the effect going to be on the analytical blank? Now, there are a number of challenges in trace metals analysis, but here are three big ones that all of us face. One, of course, is that we need to prevent contamination during any step of the trace metal analysis process. Certainly, we want to eliminate any potential interferences there may be on the analytical instrumentation caused by difficult matrices. And also, we want to minimize or actually eliminate any potential losses during the sample prep process, whether that be physical loss of sample or possibly loss of volatile elements such as arsenic and mercury during the digestion step. Now, of course, cleaning any material that comes in contact with your sample during the process is a critical step. A good general procedure that many labs use is soaking these materials in either dilute nitric or dilute HCl for a period of up to 12 hours. And for the ultimate cleaning, really that acid should be hot, especially if we are using polymer type materials, because we want to basically swell those polymers and leach out any contamination that was bound within. Now, although effective, these general procedures or the traditional way of cleaning do have some challenges. One is that it is time consuming, both from the actual cleaning process, but also the rinsing, the washing, and the drying step subsequent to the cleaning. Cost can certainly be a factor. To be effective or to maximize this cleaning effectiveness, routine changing of the acid will be required. And finally, there is, of course, a safety component, as this will expose analysts to large quantities of acid. An alternative approach that works extremely well to the traditional way of cleaning is actually steam cleaning your lab materials with nitric vapors. Now, the steam cleaning method is relatively simple. What you have is you have a container that has a large reservoir of acid in the bottom. There is a rack that contains hollow tubes, either glass or Teflon coated tubes, and the bottles, microwave vessels, the lab components are placed on top of those tubes. That acid reservoir is heated up, giving off pure acid vapors which condense on the materials and are constantly rinsing it throughout the process. This technique is extremely fast, usually being about 1 hour in total. Milestone automated cleaning system is called the TraceCLEAN. Now, during the cleaning process, the great thing is that as we're rinsing our lab materials, the trace metals or the contamination is actually remaining in the acid reservoir. Only clean acid vapors are being produced. Contamination is not traveling with them. A benefit of this approach is that at the end of the program, the materials being cleaned are dry. All right, so certainly one potential source of recontaminating vessels during the traditional approach is when they're being laid out to dry. This is not a problem here, as many labs using the TraceCLEAN actually keep the components inside until they're ready to be used. Here's an interesting slide that compares the data from doing the traditional approach of acid leaching versus steam cleaning in a TraceCLEAN of both Teflon microwave vessels, as well as the quartz vessels or the quartz inserts that Dr. Nobrega talked about earlier. As you can see from the data, the steam cleaning is as effective, if not more effective, than the acid leaching traditional process of doing this. The benefit of the TraceCLEAN and acid steam cleaning in general, I'm sure you are now well aware of. One is that it's unattended, and you can really clean pretty much anything that comes into contact with that sample during the trace metals analysis process. As I said, the program is fast, typically less than an hour, and there are preset programs directly in the controller, so you do not have to do any method development on your own. The system also eliminates or minimizes any exposure of the analyst to acid vapors. The system is PTFE coated and has a built-in exhaust system. Now, in addition to cleaning, as Dr. Nobrega mentioned, the reagents, the purity, the quality of the reagents is extremely important during the trace metals analysis process. For example, when we're doing a digestion, the amount of acid being used is considerably greater than the sample that we're actually digesting. If you think that a quarter gram of sample when we're doing a microwave digestion typically takes 10 grams of acid, it is critical that the amount of that the concentration of our elements of interest in that acid are far below the concentration of those elements in our actual sample. Now, liquid reagents, distillation, traditional distillation is the way that purified reagents. The challenge with this is that we're basically boiling the reagent, and this boiling creates aerosols, and your contamination can travel with the aerosols. An alternative technique, or a better approach, is actually sub-boiling your reagents, and that eliminates this creation of aerosols and gives you much pure acid. Simply a visual that you can see here in this slide. On the left, you have conventional distillation. Again, we are boiling or bubbling the reagent, transporting contaminants to where we're recondensing and collecting the acid. In sub-boiled distillation, we are simply gently heating the surface of the reagents, giving off purified vapors while the contaminants stay in the reservoir. Dr. Nobrega showed this slide to you earlier, and really it's quite amazing that when you look at the total contaminant level in sub-boiled distilled versus traditional distillation, sub-boiled distilled has an order of magnitude less contamination than the traditional approach. Now, a sub-boiling distillation system has a number of components to it. One, again, you have a large reservoir of acid, and this reservoir of acid is heated via infrared elements. The purified vapors are given off, and there's a cold finger that runs down the middle of the distillation unit. This cold finger condenses these purified vapors and is collected in a Teflon bottle. Milestone has two sub-boiling distillation systems available. One is called the Milestone duoPUR, and the other is the Milestone SubClean. The duoPUR is a double quartz sub-boiling distillation system. Quartz is an excellent material in general for doing trace metals analysis, as it has very low trace metal contaminants. But from distillation, quartz is an excellent material to use because it will actually get cleaner over time. Obviously, distilling your own acid has a number of benefits, but one of them is definitely cost savings. I think any lab, if they had their choice, they would use ultra-pure acid, but the cost can certainly be prohibitive. In the duoPUR quartz distillation system, it's suitable for doing nitric, HCl, as well as water if needed. In addition to the duoPUR quartz system, we also have the SubClean. And the SubClean is a PTFE sub-boiling distillation system. Once again, we're going to be saving a significant amount of significant amount of cost on ultra-pure acid. But now it's not only suitable for nitric and HCl and water, it's also suitable for HF, or hydrofluoric acid distillations. What's nice when we are purchasing ultra-pure acid is that we get a certificate with it, correct? We get a certificate that guarantees that the contamination within this bottle of acid is at or below these limits. The problem is that as soon as that bottle is cracked open, that certificate is null and void. It no longer applies. You can see here in this slide how the contamination over the course of an 8-hour day on an ultra-pure bottle of water changes drastically from the simple opening and closing of the system. What's great about the distilling your own acid, in addition to the cost savings, is that you always have ultra-pure acid available at your fingertips. Okay, so we're going to switch gears slightly here and talk about the critical role of sample preparation in trace metals analysis. If you recall from the previous slide that Dr. Nobrega showed, he showed that the most errors during the trace metals analysis are introduced during this key step. The analytical instruments of today, we can get results in a matter of minutes, sometimes seconds. So conventional sample preparation techniques are really the bottleneck in the whole trace metals analysis approach. Now, really the adage garbage in equals garbage out really applies for sample prep, because any analytical measurement is only as good as the sample prep. The ICP or the ICP-MS is only going to tell you what is in the sample that you put in front of it. Because of regulations, R&D needs, et cetera, the demand for lower and lower detection limits is increasing. And so sample prep is becoming an even greater component of the analytical process. Now, many people think, when they think of microwaves, they think the biggest benefit of microwave is that it's fast, right? Compared to hours doing hot plate digestions, we can do now digestions in an hour or even a matter of minutes. And that is certainly a benefit of microwave. But just as important is the quality of digestion that microwave provides, because we are able to go to such high temperatures. To give you an example of the effect of temperature on an actual digestion sample, is we created two test conditions. We digested the same sample type, which was ginkgo, the same sample amount, which is 0.5 gram, used the same acid chemistry and time, but in test number 1, we digested at 180 degrees C, and during that process, we reached a pressure of 32 bar. In test number 2, we went to 200 degrees C, and here reached a pressure of almost 45 bar. Now look at the difference between those two samples. Sample number 1, again, we were digesting at 180 degrees C and 32 bar. Although you can't see any physical or particulate remaining in that sample, notice the color of it. Okay, that color, that yellow color, is still undigested or residual carbon that is remaining in that sample. If you were to shake that sample, you maybe even see it become sudsy or soapy. To eliminate that problem, we needed to go to a much higher temperature of 20 degrees. And that's what you're seeing in the second sample there. The sample was done at 200 degrees, and look how it is nice, crystal clear, almost water. This is success when we're talking about sample preparation. Now, residual carbon content, having that remaining in the sample post-digestion can cause a couple of problems. One is that it can cause or generate interferences in the ICP or the ICP-MS, and it also can cause clogging because of all the soot that is created during the analysis. Here's a slide that shows the residual carbon content of 3 different samples: ginkgo, polyethylene, and heavy oil. So very different types of samples. Ginkgo being the easiest, quote unquote, easiest to digest of the 3. Look at the carbon content, how that changes with temperature. Even something like ginkgo, we really want to try to digest at 200 degrees C to minimize that residual carbon content. Now, heavy oil and polyethylene, much more stable matrices, much more difficult matrices to digest. It's not until we start to get to 240 or even 260 for heavy oil where we see that residual carbon content decrease. And as many of you know who are familiar with microwave, attaining temperatures of 260 degrees are extremely difficult. But we will talk about one instrument that can achieve those routinely in upcoming slides. So when we think about the ideal sample prep procedure, whatever it is, what are the important attributes? Well, certainly we want to be able to digest large sample masses. Although it's not necessarily the case, sometimes we need to digest large sample masses because of detection reasons, or because we need to get a representative sample. Food, for example, is notorious for needing a large sample so that we can get reproducible data. Of course, our sample prep technique must be compatible with multi-element analysis and being extremely safe. For those labs that need it, high throughput is important, and obviously data quality is the most important. So we need to make sure that we retain all of our elements of interest while minimizing the analytical blank. The Milestone has 2 sample prep instruments or microwave digestion systems for performing trace metals analysis. One of those systems is a traditional rotor-based microwave called the Ethos UP. Again, those of you familiar with microwave have seen this unit or units similar to it. And Milestone also has a unique technology called SRC, or single reaction chamber technology. And this is installed in something called the UltraWAVE, or an instrument called the UltraWAVE that you see here on the right. Now, the Ethos UP is Milestone's newest generation of microwave digestion systems. There are a number of important features about the system, but certainly one of them, when we're thinking about just the microwave itself, is that it is extremely safe. The system is completely built from stainless steel, and that is to control, in the case of an event inside of the microwave, we want to make sure that we contain and control that event. That is why we build the systems completely from stainless steel. Now, inside the Ethos UP, there are a number of different rotor options that are available to you. Our most common rotor that we provide is called the SK15 high pressure rotor. Now, this is the highest throughput high pressure rotor available. It is 15 positions. It is 100 bar and 300 degrees C in terms of its specification. The systems use Vent-Reseal technology, which Dr. Nobrega talked about earlier, and this is a patented technology by Milestone. This high pressure rotor is really suitable. It's extremely flexible, and it's suitable for a wide variety of sample types. When you're thinking about microwave, the higher the temperature and pressure capabilities of a system, the more flexible that system is. So once again, here's just a closer up picture of that SK15 rotor. Okay, 15 segmented positions, and you only run the number of positions that you're going to be using. A general rule of thumb in microwave is that as you increase the number of samples that you're digesting at a given time, the flexibility of that rotor, of those vessels, go down, simply because we don't have the ability to support those vessels at the high temperatures and pressures that are needed. In addition to the SK15 high pressure rotor, Milestone also has a rotor called the MAXI-44 that allows analysts to digest up to 44 samples simultaneously. This system is great because it's very easy to use, the handling is much easier, and you have full temperature control in all vessels. Now, although I mentioned that the temperature and pressure capabilities of this rotor is less, so the flexibility goes down, it still applies to a very wide variety of samples, such as environmental samples or easier to digest organic samples. As I mentioned, there's two ways of controlling the temperature in the SK15 and the MAXI-44. On the left here, we have direct temperature control, and that would be on the SK15, where we have a temperature probe actually inside of the digested solution, constantly giving feedback to the system so that the system knows how much power needs to be added so that you follow your temperature profile very precisely. On the right-hand side, we also have contactless temperature control using infrared that gives us the ability to monitor the temperature of all vessels, whether that be in the MAXI-44 or the SK15 at any given time, and provides profiles for every single one of those vessels during the entire length of the digestion process. Perhaps one of the best features, or let's say the most important features of the Ethos UP, is the software, okay, the easy control software. Ultimately, as chemists, what we're always trying to do is control the reaction that's occurring. Here we're digesting 1 gram of dry organic sample, something like rice, inside of an SK15 vessel. And you can see at about 120 degrees, we notice an exothermic reaction that occurred. In organic samples, it's common when a certain temperature is reached, 1 carbon bond breaks, and because organic samples are made of many carbon-carbon bonds, they all break at the same time, releasing energy, and this is where we see this exotherm take place. The important component of the Easy Control software, because it uses PID control As soon as it sees a deviation of temperature of only 1 degree from the set temperature profile, the power automatically shuts off. And that's that black line that you see on the screen here. The system waits for the temperature to come back to the temperature profile before it again begins to add microwave energy. The last thing that we want to do to a sample that's giving off energy is add more energy to it. Finally, a very important component of Milestone, really what we strongly believe in, is technical and application support. And there's a lot of it in all of the instruments that we provide. Specifically in the Ethos UP, there are over 300 pre-installed digestion methods at your fingertips. You also have the option of creating your own digestion method. Uniquely, there's also something called Milestone Connect, which is a unique feature of the Ethos UP. Milestone Connect gives you 24/7 application support. It allows you to monitor and control the microwave digestion remotely. And also at your fingertips has application notes, user manuals, tips and techniques, videos, as well as any updates to the system, again, all through Milestone Connect. So lastly, just to summarize the Ethos UP, it is suitable for a wide variety of different sample matrices and can digest up to 1 gram of dry organic material. With the MAXI-44 rotor, it is a very high throughput system, but even the SK15 is the highest high pressure rotor available. It's easy to use and has a lot of safety features built in from the stainless steel chassis, as well as other features such as a vent and reseal actual door of the microwave system. Now, with all technologies, there are, let's call them, some limitations or some challenges. And with traditional microwave systems, whether it be Milestone or other manufacturers, there are some challenges with these rotor-based microwaves. And those challenges are that you need to batch like samples together. You need to run the same chemistries on all vessels at a given time. There's a fair amount of vessel handling that takes place, both assembling the vessel and disassembling a pressurized vessel at the end of the run. And you also have a fair amount of, well, you do have cleaning that needs to take place because you have to clean those Teflon or quartz components in between runs. Finally, because we are doing digestions inside polymer type materials, fluoropolymers, we still do have limitations in terms of the temperatures and pressures that can be achieved. And that's why Milestone introduced the UltraWAVE using SRC, because it specifically addresses all of those challenges of traditional rotor-based microwave systems. At the heart of SRC, or single reaction chamber, is a 1-liter stainless steel reaction vessel. There is a sample rack that is lowered down into this reaction vessel, and one of the key components, or the keys of SRC technology, is that this sample rack is actually sitting in what we call a base load. It's a base load of water. And we're not controlling the temperature of any individual vessel, we're controlling the temperature of that water. And by doing it in this way, this allows us to digest any mix of samples at the same time. Polymers and soils can be digested successfully and safely at the same time. You can use any different chemistry. You can do digestions with nitric, aqua regia, HF, all in the same run. And not only do it safely, but ensure that all of the samples are reaching the same temperature or being exposed to the same temperature and pressure. This is a first in microwave digestion. Another key concept with SRC is that before the start of the run, the whole chamber is pre-pressurized with nitrogen. What this allows us to do is use very easy to use vessels with simply loose fitting covers. By pre-pressurizing, we immediately raise the boiling point of the reagents on the inside, which allows us to avoid both sample loss as well as loss of traditionally volatile elements, mercury, arsenic, etc. Here's the digestion sequence of using SRC technology and the UltraWAVE. In step number 1, we're simply going to be placing the rack on the lid of the unit. That rack is going to be lowered down into the chamber and sitting in a bath of water. We're going to pre-pressurize with nitrogen, typically up to approximately 40 bar. We're going to apply the microwave energy. At the end of the run, a great thing about SRC is that the system automatically depressurizes for you. When you're doing a traditional microwave run, as you all know, at the end of the run, you take the rotor to the fume hood, but you still need to open up those individual pressurized reactors. In the UltraWAVE, that is automatically done for you, so when that sample rack comes back out, those samples are ready to be post-processed, diluted, and ran immediately on the ICP or ICP. Here we have a picture of the two most common sample racks that are available for the UltraWAVE. There is a 15-position 15 mil sample rack, as well as a 5-position 40 mil sample rack. Both racks have vials that come in both Teflon, quartz, as well as disposable glass. And interestingly, although disposable glass is not the best material for doing trace metals analysis, it does work extremely well for many elements. I would say the only elements that it does not work very well for, let's call them, are the traditional environmental contaminants: sodium, potassium, calcium, aluminum, magnesium, things of this nature. For all the heavy elements, for all the elements even described in the new USP chapters, disposable glass vials work extremely well, and of course, that eliminates the cleaning step altogether. To illustrate what I was just mentioning in regards to contamination, the blue lines are glass, the red line is contamination in quartz, and the green is in Teflon. As I mentioned, there are certain elements that if you are analyzing, glass is not going to be an option for you. But note, for many of the elements in the suite we look at here, glass is perfectly suited for even doing ultra trace metals. Once again, the UltraWAVE provides a significant increase in workflow efficiency. On the left-hand side, if you were digesting samples such as needed to digest fish oils, polymers, and ginkgo, what would happen is that you'd have to do 3 individual separate microwave runs. In the UltraWAVE, because of we're using that water bath, we do not have any single control vessel, we can digest all of those samples simultaneously. In addition to that, we can also run blanks and SRMs all together. So once again, for the first time, we can run blanks, samples, and SRM materials and expose them and know they're being exposed to the exact same temperature and pressure conditions. You know that the UltraWAVE has a lot of benefits to it, but the true power of the UltraWAVE or SRC technology comes from its flexibility. For those of you, again, experienced with microwave, you know that there are systems available that are easy to use. There are systems designed for very high throughput, designed for high temperature, high pressure applications. The UltraWAVE, however, is one system that can handle it all. You have very easy to use vessels, and also because of the high temperature, high pressure capability of the UltraWAVE, 300 degrees C and 199 bar, what many users do is that they have one digestion method for all of their samples. They do not have different temperature and time programs for different matrices. They simply use one that encompasses it all. The UltraWAVE, both because of the speed of the run, but also just the minimal handling that is required, is extremely productive. And sure, it has a higher initial cost involved. Over the long term, the operating costs of the UltraWAVE are much less than traditional rotor-based systems. So that is it for my portion of the presentation. I wanted to thank everyone for attending today, and I hope that you found the information that Dr. Nobrega and I presented useful. Back to you, Laura.
Thank you very much, Tim, for that excellent talk, and thank you, Dr. Nobrega, as well. Okay, it is time for Q&A, and we have a lot of questions already, so let's dig right in. But as a quick reminder, if you want to submit a question, you can do that by using the Q&A box, and you can find that on the right-hand side of your window. Okay, first question. If we digest a sample of pure chrome powder, should we expect this to be clear as well?
So always when you're doing digestion, the goal is that we want a clear solution and particulate free. However, keep in mind that there are some elements that will cause the solution to be colored. Blue, red, sometimes green. Color is okay because that is the element actually in solution. But what we don't want is particulates. If we have particulates, we are not sure that we have all of our elements into solution. So colored is okay, which you may have when you're digesting chrome. However, we do not want particulates remaining at the end.
How do you know a digestion is total or complete? By just looking at it?
That's a good question. Yes, that is certainly a common way of doing it, is by looking to see if there's any actual particulate matter remaining. But to be sure, we just have to, or we should be employing good scientific practices, doing your digestions in duplicate or triplicate. If we are having incomplete digestions, we would expect our RSDs to not be very good. Certainly by checking with SRMs, and SRMs that are similar in matrix to our actual sample that we're looking at. That's really the best way, or the only way that you can be sure. A good visually, it's a good start. You know, you can say, wow, this method seems to work, but to be sure, you need to check the reproducibility and the accuracy of the SRMs.
Can you explain why the color of the ginkgo digest is yellow? Is that caused by residual NOx?
That's a great question. Yes, sometimes when you are, well, oftentimes if you are digesting samples that create a lot of pressure, when you open them up, you will have a greenish hue to the sample. However, that upon dilution, if it's NOx, that NOx will get released, and that solution will clear up. In that ginkgo slide that we showed earlier, that even after dilution, we still had that yellowish color remaining. And anytime you have this yellow color, or oftentimes a sample could cloud up, it looks clear upon immediately after digestion when it's hot, but as soon as you dilute it, it clouds up. That is, in fact, undigested organic material. And if you also recall from the slide that I showed the different residual organic carbon contents for heavy oil, polyethylene, and ginkgo, you noticed a big drop in residual carbon content from 180 to 200 degrees C for ginkgo.
How large a sample can be digested in a single SK15 vessel?
That's a great question, and that's a question that we get a lot. And unfortunately, there's no black or white answer because it depends so much on the matrix itself. If we would be talking about foodstuffs, rice, dried rice, perhaps biological material of some kind, tissue and so forth, naturally occurring organic materials such as these, 1 gram, I think, is a pretty good maximum estimate that you could digest. However, on the other end of the spectrum, you have much more difficult organic matrices that are much more stable. Again, heavy oils and polymers. These two materials are almost the nemesis of microwave digestion, and I say that because they are both stable, so they require a fairly high temperature to break them down, again referring back to that slide that I showed regarding the residual organic carbon content. But because they are organic, they also create a fair amount of decomposition gas during the digestion process, specifically NOx, carbon dioxide, etc. For heavy oils and polymers, I would say in an SK15 vessel, somewhere in the range of a 1/4 gram is usually safe. A 1/2 gram, you're really starting to push it. Some easier to digest polymers like nylon or some lighter oils and so forth, you can get into the 1/2 gram range, but really a 1/4 gram is where I'd shoot for.
Has the UltraWAVE system been applied to rock samples? And does it digest normally acid-resistant minerals?
That's a great question. There are some of the toughest samples to digest traditionally are geologicals, zircons, and, well, specifically zircons, but there are a number of other refractory materials. You know, again, it's not a black or white answer, but what I can tell you is that in the UltraWAVE, we have customers that are digesting samples at 270 degrees C and holding at these temperatures for 30 minutes. And this is far greater than any traditional microwave system where you would max out at 220 or 225 degrees C. So I would most likely say that the UltraWAVE cannot encompass all geologicals or similar refractory type materials, but it definitely is more flexible, has the ability to digest a wider range of these types of matrices simply because of the higher temperature that can be attained.
So are you recommending that ultra-pure acids always be used for digestion?
No, not at all. Ultra-pure acids would only be needed. It depends so much on your the detection levels that you're needing to see. Okay, it goes back to that slide that I mentioned before regarding the quantity of acid relative to the sample size that you're using. Typically, ultra-pure acids are used from individuals using ICP-MS specifically, and looking at very low levels of detection in the low ppb, ppt range. At this point, you know, ultra-pure acids, the benefit they give is one, you can get accurate data, but it also eliminates one of the variables in terms of contamination that you have to keep in mind. So no, ultra-pure acids are not always recommended. Certainly there are plenty of labs that are using trace metal grade acid for doing trace metals analysis. It really depends on the levels that you need to achieve.
What quantity of organic material is recommended for each vessel size in the UltraWAVE?
Great question. So we'll talk both about the 15-position rack as well as the 5-position rack. And again, because organic matrices are so diverse in the types of organics that they are, it's going to vary quite a bit. In the 5-position rack, we obviously have the ability to digest the most amount of organic sample per vessel. And we've digested as much as 5 grams of organic sample in each one of those vessels in a given run. But this organic material would be, again, something like the foodstuffs, the biological materials, the clinical type organic samples, these types of materials. When we're looking at polymers and oils, again, on the very difficult end of the spectrum in terms of organics, now we're talking about a half a gram, possibly even pushing a gram in each one of those vessels, again, in the 5-position. In the 15-position rack, anywhere from a quarter gram to a half a gram of organic material would encompass most applications.
How long does it take to run the digestion in the UltraWAVE?
Yep. Yeah, so the UltraWAVE is extremely fast, and it's not fast necessarily because of the program. And what I mean by that is that if you need to digest your sample at 240 degrees for 30 minutes, there's no difference between that and using another system. However, where the real speed comes with using the UltraWAVE is that entire sample prep process. For example, when we are weighing our samples, all we are doing is weighing them into a tube and putting a loose fitting cap on top. There's no cranking down of vessels. There's not 6, 7, 8 components to each vessel. It's only 2, so assembly is very easy. We can attain temperature very quickly in the UltraWAVE. It's a 1-liter pot, and it's a 1500-watt microwave. So it's a very dense microwave field that allows maximum energy to be absorbed by that base load that allows us to get to temperature very quickly. Once again, as I mentioned before, once we're at temperature, it's not necessarily a time savings. The only caveat I would say to that is if we're digesting samples in a traditional system at its max, for example, 30 minutes at 220 25 degrees, which is again is the max on a traditional system, we can probably actually digest it much faster in the UltraWAVE because now we'll go to 250 or 260 degrees C. Finally, at the end, when the microwave program is finished, the system has a chiller. And so we cool down from 250 degrees to 80 degrees C in as little as 12 minutes. And once it reaches a set point temperature of that 80 degrees C, the system automatically depressurizes itself for you. So I would say because of all this, from the time that you actually put the samples into the UltraWAVE to the time that they are removed, completely depressurized, ready for post-processing, average would be about 50 to 55 minutes. Whereas a traditional system, I would say with cool down and depressurization and so forth, we're looking at an hour and a half to 2 hours.
For the digestion of food materials, what minimum conditions would you recommend in terms of temperature and pressure, et cetera, as a starting point to get consistent results?
Yeah. You know, with food, they're made of proteins, fats, and carbohydrates. And each one of those have different temperatures in which they break down at. The most difficult of those three that I mentioned are fats. They're the most difficult to break down and to digest. I would say the minimum starting conditions for digesting food is 180 degrees C, but ultimately I would typically recommend doing at least 200, if not slightly more than that.
If you're using the microwave program for 15 vessels, is it okay to use fewer than 15 vessels?
Absolutely. Yes. In the UltraWAVE, you're only going to use the number of vessels needed to perform the actual run. If you only need to digest 2, only put 2 inside of the system.
Is it possible to use disposable digestion tubes in these digestion units?
Absolutely. That is one of the big benefits of the UltraWAVE, is that you can use disposable glass vials that are pennies a piece in the system. Now, choosing the material needed for doing the digestion depends on a couple things. One, of course, is the acid that you're going to be using. If you're needing to use HF because there's silica, titanium, or other such elements in your sample, then of course you must use Teflon. If you, the other thing you have to ask yourself is the levels that you need to reach. If you're looking at sodium, again, these common environmental contaminants, quartz or Teflon is the best to use. For heavy metals, toxic heavy metals, lead, mercury, arsenic, and these, glass is great to use, and it works really, really well, and you can achieve ultra low levels of analysis.
Is each digestion tube self-contained and sealed the entire time during digestion?
In the UltraWAVE, no. Actually, the individual tubes themselves have loose-fitting covers that fit on top. And this is a common question that we obviously get, is that there's a fear of loss of volatiles or crossover contamination. But what I remind you is that, remember, before we start the run, we pre-pressurize the unit with nitrogen. And that pre-pressurization, of course, raises the boiling point of the reagents that are being used, but it also changes the characteristics or the properties of the elements of interest or the analytes that we're looking at. Okay, the boiling point of arsenic, for example, under pressure goes much higher. And so we've done multiple studies looking at possibilities of loss or crossover contamination, even with loose-fitting covers, and there is none. And that is, again, attributed to the pre-pressurization at the beginning of the run.
Let's just do maybe 1 or 2 more questions, and then we'll wrap up. Is the quality of nitric acid obtained with the SubClean similar to that obtained with the duoPUR?
Yes, it is. Yes, it is. There is no noticeable difference between the quality of acid between the duoPUR and the SubClean.
Excellent. All right. Well, we went a little bit past the hour, but we had so many good questions I thought we should. But I think we should wrap it up now. Tim, thank you so much for answering all those questions.
You're welcome. Thank you.
I'd also like to thank all of you in the audience today for watching today and for participating by asking all those good questions. I'd also like to thank our sponsor, Milestone, for making today's webcast possible. This webcast will be available for on-demand viewing through January of next year. You'll receive an email message from Spectroscopy alerting you when the webcast is available for replay. We invite you to forward that announcement to your colleagues who might have missed today's live event. We hope to see you all next time. Goodbye.